Chapter 25, Electric Potential. We have so far discussed electric fields and electric forces. But starting from this chapter, we're going to look at the energy aspect associated with electric field and electric forces. We know when it comes to the gravitational force, we can introduce what's called gravitational potential energy because, as we learned in Physics 1A and 1B, the gravitational force is what's called a conservative force, right? For any conservative force, one can always define a potential energy associated with it. So there is something called the gravitational potential energy. Is there such a thing as electrical potential energy? Well, it depends on whether the electric force is a conservative force or not. And you can probably guess, based on the great similarity between the electric and the gravitational force that we emphasized in the previous two chapters, it is very likely that the electric force is also a conservative force, and we can introduce something called electrical potential energy. Now, let's make sure we can do that. First, let's do a little review of Physics 1A. What does it take for a force to be labeled as a conservative force? Well, we use a subscript C to denote a conservative force. For a force to be conservative, as we learned in Physics 1A, it must be such that when you take that force and you move around any self-enclosed contour C, this C can be of any shape as long as it comes back to itself. Okay, then Fc dot ds, ds being the little displacement along the contour, the integral would be 0, which means the total work done by this conservative force along any self-enclosed path would have to be 0 for that force to be called a conservative force. That is the definition of a conservative force. Now let's see if the electrical force, which satisfies the Coulomb's laws, satisfies the requirement of being conservative. Here, as you see, is the electric force exerted by a charge Q1 on a charge Q2. Okay, we have a charge Q1 here, and we have another which is fixed. Then we have another charge Q2 which moves around in an arbitrary path. The distance between Q1 and Q2 is r. Okay, so we have a vector here from here to there, and that is the r vector. So it's k q1 q2 over r squared, and here's the unit vector along the r direction. Let's see if I move q2 along its path with a little displacement ds, okay, which may not be along the r direction. What is f dot ds equal to? As you recall, this is dw, in fact, the work done by this force on q2 as it moves a distance ds. Okay, so that is f dot ds, right? And then we can plug in the value of f here, which is this whatever value that is, k q1 q2 over r squared, and then you have r dot ds. Now let's take a closer look at r dot ds. Okay, r, as you know, is the unit vector along this direction, along the radial direction connecting q1 and q2. That's r, and then ds is that way. The angle between them is theta. Of course, this theta can change as q2 goes along a variable path. But if we are going to take a closer look at r dot ds, here is, let me draw a bigger picture here. This is the unit vector r, and this is ds. Okay, this is ds. This angle is theta. What exactly is r dot ds? That would be r times ds times cosine theta. R has a magnitude of 1, so really r dot ds really is just this length, right, from here to there, because this is ds 90 degrees, and here's the angle theta, so r ds cosine theta is just that. But wait a minute, what is that? That really is the change in the radial position of this charge q2 from here to there. It has a displacement when it went from here to there, but radially, okay, along the radial direction, how far did it move? It moved from here to there, right? And let's call this radial displacement dr. You know, that is not the same as ds, because ds goes that way, dr goes that way. So this dr is a scalar. Okay, it just tells you the change in the distance between q1 and q2. Okay, it went from r to r plus dr. This dr could be positive or negative even if it goes closer to q1. So with that, let's find the integral of dw. Okay, let's calculate. That's ke, and then q1, q2, these are just constants. right? And then what's left is 1 over r squared, 1 over r squared, and then dr. Alright, now let me integrate over a self-completed contour of any shape, okay? And that's a contour. So tell me, after you go around, what is this integral equal to? Well, you can work out this integral. It's very simple, dr over r squared. So it's just negative 1 over r when you work it out, right? And since you go back to yourself after one complete trip, the upper and lower limits of r will be the same, right? So this integral after one complete contour is actually equal to 0. Okay, I should integrate it here as well. So, indeed, as we suspected, the Coulomb force, the electrostatic force, satisfies this condition. Okay, satisfies this condition. In other words, it is a conservative force. Now, of course, we only showed that for the force between 2 point charges. What if this is not a point charge, rather it's a whole bunch of charges? Can we extend this result? Well, all we have to do is to use the superposition principle. Suppose this is not just a single charge Q1, rather it's got 10 charges. Okay, it doesn't matter, because then you just find the force between the first charge and that moving charge, and the second charge and the moving charge, the third charge and moving charge, and for each one of these forces, I found that the net work done by that force is equal to 0. Okay, and you add all these forces up, the net work done by all these 10 forces would still be 0, which means regardless of the charge distribution here, doesn't have to be a point charge, the net work done by all these charges on a moving charge, as that moving charge goes around one complete contour, always equals 0. And that is to say that the electrostatic force, or the Coulomb force, is indeed conservative. So what's so good about the force being conservative? As you might recall from Physics 1A, okay, this is the reason why we're so interested in a conservative force. For a conservative force, you take any complete contour, the net work done is 0. Now let's say we break the contour into 2 segments, the green segment and then the red segment. Okay, so it tells us that the work done going from here to there plus the work done from here back to there is 0, right? So let's say the work done from here to there is W1, okay? And then the work done from here to there is W2. It is clear that W1 equals W2 because you go from here to there, the work done is W1, and you go backwards, the work done is negative W2, right? So, but W1 plus negative W2 equals 0 because the force is conservative. That means W1 equals W2. Now remember, these are 2 arbitrary paths joining the initial point and the final point. And the work done on any charge, whether you move along path 1 and path 2, are the same. And that tells you that the work done due to electrostatic force on any moving charge going from a certain initial position to a certain final position is independent of the path, because you choose whatever 2 paths, you get the same amount of work. Okay, so again, W, the work done on any charge under the influence of electrostatic force going from initial to final, is a function of I and F, these 2 points only, but it's not a function of the path. In other words, you can take this green path, you can take this red path, you can take any path you want. Because of that, one can then define the work from initial to final, define as a function of initial and final positions only, not a function of the path. So we can define it as a function u initial minus a function u final. You see, there is no information here on the right hand side about the path. Okay, we can only do that because it's a conservative force. Otherwise, W1 and W2 would be different, and then you cannot define it only as a function of initial and final position. You have to also tell me exactly which path it took to go from initial to final. Okay, of course, the work done is the integral of F dot ds, right, from initial to final. So this gives us a definition of the potential energy function U, such that the work done on that charge going from initial to final by an electrostatic force equals the initial value of the electrostatic potential energy minus the final value of the electrostatic potential energy. Now, why did we put initial ahead of final? You might say, well, that's how we define it. But is there a reason why we define it like that instead of final minus initial? Well, it's because we learned from physics 1A. The potential energy is defined such that when that conservative force does work, okay, it does work. It does so by spinning its potential energy. All right, so you start with initial value of potential energy, UI. You end up with final value of potential energy. Okay, how much energy did you spend? It's U initial minus U final. Okay, it's not U final minus initial because that would be the amount of potential energy you gained, not the amount of potential energy you spent. All right, so you spend potential energy and you do work. Of course, that work can be turned into kinetic energy. So that would lead to the conservation of total energy, as we will see later. Okay, so this U is a special form of potential energy in association with electrostatic force. So we call it electric potential energy or electrostatic potential energy. Okay, you can see here U is directly proportional to the work done, which in turn is directly proportional to the force, which in turn is proportional to the amount of charge, okay, that this particle carries. It's not just proportional to the strength of the field which causes this force. It also is proportional to the strength of test charge, right? So naturally, just like we did for the electric field, we want to eliminate the inference of the test charge. So what we're gonna do is we're gonna define a new function, V, not U. V is defined as U over Q naught. What's Q naught? Well, Q naught is the test charge that we use to test the strength of the electric field. Okay, so if U is proportional to Q naught, then the ratio of U over Q naught is not a function of Q naught anymore. Okay, it depends only on the strength of the source which creates the electric field. So if you take this, you divide every term by Q naught, divided by Q naught, Q naught, Q naught. What do you get here? U initial over Q naught, that's V initial, right? And U final divided by Q naught, that's V final. And then here you have to take F, the electrostatic force, divided by Q naught, and that, as you know, is the electric field. Okay, so this formula tells you how one relates the electric field E with a scalar function called the electric potential, not electrical potential energy. Okay, please be careful. This is the electrostatic potential energy, and here's the electrostatic potential. They're not the same. Okay, so once we know E, we integrate, we will get the difference in potential, the electrostatic potential. Okay, so this is the general formula, how we calculate electrostatic potential. Okay, so with that, we're now going to calculate V for some special cases. And which case do you think we should start with? Well, let's start with the simplest of the electric field, which is the electric field produced by a point charge. Okay, so I'm going to retain this formula here, and let's see how we can calculate V for a point charge. So here's the point charge in question. Okay, and in order to find V initial minus V final, we're going to follow this formula. Okay, you go from initial to final, any path. Okay, the path doesn't matter as long as you go from initial to final. Any path would do. All right, E dot ds. Now, here's the thing: as you move along an arbitrary path from here to here to here to here to here, does the electric field stay as a constant? Well, of course not, right? The electric field is always starts from here and it points, radially away from it. So the direction of the magnet will both change if you choose such a path. Now, since any path will yield the same result, why don't we pick the simplest possible path to do the calculation, right? Okay, so the question is, which path do we take? Okay, many of us would just think, well, if it's the simplest path, let me just join initial and final as a straight line, right? Okay, that may be the easiest to draw, okay? But is it the easiest to calculate? Well, suppose I draw a straight line connecting initial and final. Then as I move along that straight line, tell me, does the electric field stay as a constant? Does it vary in magnitude and direction or not? Well, actually it does, both in magnitude and direction, right? As you move along like that, Q will produce an electric field that's always radially pointing away from it, so therefore both the magnitude and direction of the E field will change if you draw a straight line. So the straight line may be easy to draw, but it may not be easy to calculate. Okay, so what kind of path should I take? Well, you know, if you move radially away from Q, you get one advantage, and that is the direction of the electric field produced by Q will not change, right? So why don't we start from here? And I'm going to move radially away, like this, okay? Now, if you move radially away from here to there, what happens to the direction of the electric field produced by the charge Q? Nothing. It stays that way. So that's one simplification, okay? But of course, I must join initial and final. If I keep on going that way, we'll never reach that final point. So how do I reach the final point? Well, at some point, I'm going to have to make a turn, okay? I'm going to have to make a turn in order to reach the final position. What do you think is the cleverest way to make such a turn? What path should I take? Okay, let's call this segment 1 and that segment 2. So for segment 1, it's a straight line moving away, pointing away from Q. What about segment 2? Well, you know, the charge produces a radial electric field, right? But if I move tangential, in other words, if path 2 is part of a circle centered at the charge Q, then everywhere along path 2, E is radial and ds is tangential, so they're always perpendicular to each other. And what's the advantage of that? What's E dot ds? What's the angle between them? 90 degrees, right? So what's E dot ds? 0. Okay, so you see the easiest thing to do is to break the path into two segments, one straight line and one arc. And the force, the integral of E dot ds along the arc is just 0. You don't have to worry about path 2, just path 1 from here to there. Okay, very good. Now we are ready to go. We say, for this special case, you choose that particular path, V initial minus V final, is simply equal to along path 1, okay, from here to there only. E dot ds. Okay, very good. Now, along path 1, first of all, E and ds have the same direction. They're both reading outwards, so it's just E ds. But ds is just dr in this particular direction, right? It's just dr, E dr. That's it. Both are just scalars, okay? And how does r change? Well, from here to there, the distance is called r initial. And from here to there, the distance is called r final. But remember, this is part of a circle centered here. So the distance between here and there, and distance between here and there, they're really the same. Either way, I call it r final, okay? Now, the next step is quite simple. All you have to do is to plug in the value of E, the expression for E. The electric field produced by point charge centered right here, and we can easily finish that calculation now. It is K Q over R squared, and then dr. Okay, well, that's quite simple to calculate, so let's write down the result. The result is K E Q R initial minus K E Q R final. Okay, now as you know, the integral gives you negative 1 over r, right? But since we're going initial to final, we flip it around, then the negative sign cancels. Okay, so this is our first example, how you calculate the electric potential for point charge. It says initial minus V final equals this function minus that function. So naturally, you would conclude that V as a function of r, the electrostatic potential produced by point charge of charge Q, a distance r away from it, is equal to what? Okay, K Q over r. Okay, that will certainly satisfy this equation. But of course, as you learned, as recall from Physics 1A, when it comes to potential energy, the 0 point of potential energy can be defined any way you want, because just like what we learned before for gravitational potential energy, as long as the difference stays the same, okay, the potential energy itself, or just like in this case, the potential itself, I can always add a constant if I want to, as long as I keep the difference the same. Okay, so you can add a constant here and the same constant there. Nothing happens to the difference. So the general expression for the electrostatic potential produced by a single point charge would be something like this. Sometimes I choose the potential to be the constant term to be 0. Sometimes I don't. Okay, that's our first example. So what happens if you have more than one charge. Okay, so you have what's called a set of discrete charges, not just one charge. Well, that's quite simple to extend. For each charge, I can find its own potential at point P. Okay, for example, the i's charge, the distance r sub I, and then the electrostatic potential produced by this guy at point P, as you know, is k qi over ri. Right? We learned that. There is also a constant, but we can forget it for now. And then since the electric fields can be added linearly due to linear superposition principle, each field produced by each charge produces its own potential, so the total potential is just the sum of the individual potentials. So that's V. Okay, V total at point P. Okay, of course I can add a constant if I want to. So that's how you extend it to a bunch of charges. And in the case of continuous charge distribution, what I can do is just like we did before. Okay, I choose an origin here. This is the dq. Okay, a infinitesimally small part of the source, and this is r prime, and as you know, this is r to the power this is r minus r prime. And let me first figure out the electric potential produced by dq, an infinitesimally small charge, and that will be dv equals k dq over that distance, which is r minus r prime, absolute value, right? And then all I have to do is to integrate, so v would be equal to the integral dq over r minus r prime, right, plus a constant. So that is how you calculate the potential of a continuous charge distribution. Alright, why are we interested in calculating the potential? It's because potential, once we know the potential distribution, then we can immediately figure out how much electrostatic potential energy a particle may have, a charged particle may have, if we put that particle at a certain spot. Okay, that's one reason. Of course, once you know the potential energy, you can do a lot of things that you learn in 1A. But another reason is, once we know the electrostatic potential, we can also figure out the electrostatic field, E, itself.